So see, we already saw what a laminar flow is. Now we'll be seeing what a turbulent flow is. When Reynolds number Re is greater than 4000, flow is turbulent flow. So this I already told you earlier when dealing with flow through pipes and everything. So this is the basis of how a turbulent flow forms. In laminar flow, we saw that this is the center of the pipe and these are the walls of the pipe. Then the profile of velocity is something like this. Here this is the value of V maximum, and this is V is equals to 0 on both sides of the pipe of wall. Now when you come to turbulent flow, this is not quite it seems. Turbulent flow, the profile is more flatter. Like if these are the walls, the green color is the walls and white color is the center line, then your profile will be somewhat like this, which means the profile is flatter than that of laminar flow profile. Now this profile variation, it depends on the Reynolds number. Say as Reynolds number increases, the profile of turbulent flow becomes more flatter. Means, see, I'll take another color to explain to you. If Reynolds number increases, then the profile will become like this. See, more flat. If it further increases, say another color, then it will go even beyond that, become like this. So Reynolds number in blue color is greater than the Reynolds number in red color, which is again greater than the Reynolds number in white color. Okay, so as Reynolds number increases, the profile of turbulent flow becomes more flat and flat. This is the main concept. Now, in turbulent flow, the important point or the main distinguishing feature of a turbulent flow is the velocity and pressure do not remain constant over time, which means if you take a particular point in a flow, say this point, then with time, as time increases, the velocity and pressure won't be constant there. And if you take more and more time, then the velocity and pressure will keep on changing. So what happens is because of this velocity and pressure not being constant over time, there are large scale eddies that are formed due to this large scale eddies. What is large scale eddies? Eddies is the current generated because of higher amount of velocity fluctuations. If a particular value fluctuates and if there is current generation because of that, then that particular thing that is generated is called eddies. So here there is velocity fluctuations. Velocity fluctuates very highly in turbulent flow. So because of that, large scale eddies are formed. Because of this, flow is completely mixed. Means each and every point in the flow is completely mixed. There is no distinguishing between one layer and another layer. In laminar flow, each layer goes in its own way, in its own path, whereas in turbulent flow, all gets mixed up. Okay, so if you can notice this profile in laminar and turbulent flow, see here it converges to the center point, reaches a maximum and again goes to 0, whereas here it increases but stays constant over a particular area and then again decreases. Same goes for this profile also, which means this happens because of the complete mixture, I mean complete mixing of the fluid. Because of complete mixing, what happens, there won't be a single point which will have maximum velocity. Many points they get mixed, so what happens, many points will have almost equal velocity because they are all mixed, they are all together at one particular area. Every particle are flowing as one single entity, so that's why over a particular area there is a maximum that exists. Because of this highly random flow, highly erratic behavior of the particles, there is no practical analysis of turbulent flow. We cannot analytically solve a turbulent flow problem. But we have to solve a turbulent flow problem because that is what happens in reality. In reality, your turbulent flow is the one that happens actually. Laminar flow is just for our calculations, but in reality, turbulent flow happens. So we have to prove how a turbulent flow behaves. So for that, what we do is we adopt a well-known approach, that is the average value approach. What is this average value approach? Is, say you are riding a car, okay, from your home you are going to a certain place that is 10 kilometers from your home. What happens is, right from the moment you start your car, you accelerate, you keep on accelerating. It's not like your velocity stays constant. No, at one point you'll be having 20 kilometers per hour speed, the next instant it will be 22 kilometers per hour, after a while it will goes to 40, after a while it goes to 50. You keep on increasing the accelerator. And again, same way you apply brake also, for a time you apply the brake. So what happens, from the starting, when you have when you apply the brake, say you have 80 kilometers per hour, by the ending you'll have some 20-25 kilometers per hour, and this reduction in speed happens over a time. Say you are applying brake for 10 seconds, or 10 seconds the value decreases from 80 to 20 to 25. So which means that for every instant there is a particular value of velocity. Each and every instant of time velocity changes. That is instantaneous velocity. But what we do, we take the distance we traveled and divide it by the time we took for travel, and we say this is the average velocity. On an average, I went through at this particular velocity. That is what we say, right? Even though we have instantaneous velocity throughout our travel, we take the average value. That same value we are applying here. We are applying that same method here, and we solve the values that we have to derive in a turbulent flow. Okay, so now we get into the actual derivation. So the first part is, okay, so now see, as I told you, there is large amounts of velocity fluctuation in a turbulent flow. Because of this velocity fluctuations, what happens, there is a complete mixture of fluid. What happens when complete mixture of fluid happens is, say you take a particular pipe, okay, these are the layers of fluid inside the pipe. What happens is, I'll zoom in for your convenience. One particle, because of complete mixing, particle over here jumps here, particle over here can jump to here, particle over here can jump to here, particle from over here can jump to here, which means complete mixing. One particle won't stay in a particular line, it will keep on jumping there. This is turbulent flow. In laminar flow they all go in a straight line, but in turbulent flow they jump between layers. What happens is, if one particle from here travels here, it takes mass along with it, which, if you consider a particle of certain density or certain area occupied, it will have certain mass, no? So when that travels from this layer to this layer, what happens, the mass from one layer to transfers to another layer, which means there is transfer of mass. When you consider a layer, there is change in mass. We don't know what particle jumped into this layer. It may be a heavier particle, it may be a smaller particle. It means there is a change in mass. And since these particles, fluid particles, are traveling with a particular velocity, we can say that there is transfer of velocity also. There is transfer of mass, there is transfer of velocity, which means there is a transfer of momentum. In turbulent flow, there is transfer of momentum. Okay, what does transfer of momentum mean? See, transfer of momentum is change of momentum. If you consider one layer, there is change of its momentum because different particles come with different velocities. So the initial momentum of that particular layer changes. There is change in momentum. According to Newton's second law, what is change of momentum? Change of momentum is equals to force applied, which means this change in momentum between these layers results for force on particular layer. Okay, now we are going to calculate that force. That is how we are going to calculate. Now, since because of this additional amount of momentum transfer, mass transfer, velocity changing, all these velocity fluctuations, there is an additional stress developed. See, there is an additional force developed because of this velocity changes. Because if we have force, it means we have a stress also, because force per area is stress. So there is additional shear stress that's being generated. This stress, additional shear stress, is only particular to turbulent flow. There won't be any such stress in laminar flow. So when we take a turbulent flow, say tau total, that is the total shear stress in a turbulent flow, is tau viscous plus tau turbulent. This is viscous shear stress. Okay, now this is turbulent shear stress. Okay, this is a starting point of our equation derivation. We will call this equation as 1. See, what I taught you in class and what I am teaching you right now, they are little bit different, the equation numbers and all, everything, but you get the idea. I am uploading this for your convenience only. So now we already know what tau viscous is. Tau viscous, let's say it is tau v is equals to mu du by dy. That we already know. We'll consider this equation as 2. Okay, just for our reference. Now, to calculate this particular forces or shear stresses due to turbulence that has been generated, there are many theories that are in existence, but we will be considering one particular theory. That theory is proposed by a scientist named J. Bosinesk. Okay, according to him, tau turbulent, we'll call that tau t is equals to eta dou v by dou u by dou y, that is equals to rho epsilon du by dy. If I have attended my class, this will be even more easy to understand, but I'll try to explain. Eta here is absolute or virtual or eddy viscosity. Epsilon is the same thing. I'll copy this. Absolute or virtual or eddy kinematic viscosity. See, this value is, let us assume this as equation number 3. See, this value over here, eta, is synonymous to mu. Why? Because here eta du by dy and here mu du by dy, they are equal. That is why they are called absolute or virtual or eddy viscosity. And we know mu is equals to rho nu, where nu is the kinematic viscosity. Nu is the kinematic viscosity, and that's the same here. Here it is rho epsilon, and epsilon is synonymous to kinematic viscosity. That is why it is called as absolute or virtual kinematic viscosity. So till here we know what it is. Now what we'll do, we'll substitute equation number 2 and 3 in 1. what do we get? Tau total is equals to mu du by dy plus eta du by dy. This is one particular equation. We'll call this as equation number 4. See, we derived this. That's fine. Everything is fine. But the main concern with this equation, which the scientists and all the engineers and all had, was this eta value. No, this is not constant. So eta value is particular to turbulent flow. What happens means eta can vary from 0 to some say thousands into mu, which means it can vary from 0 to 10,000 into mu or 100,000 into mu, whatever it is. 0 is particular to laminar flow. Okay, when it is a laminar flow, eta value is equals to 0. When it is turbulent flow, depending on how high the turbulence is, the value of eta varies from 1, 2, 2, 3 to thousands into mu. When it is a laminar flow, eta is 0. When it is a turbulent flow, this value becomes so small, only we will consider this value. That is the importance. Which means from this what you can say is, we all know mu is a fluid property. Mu is a fluid property. It doesn't change. As far as our fluid mechanics problems is concerned, it doesn't change. Mu only changes when there is a change in temperature. Change in temperature. But in our fluid mechanics problems, what we don't deal with change in temperature. We take a particular temperature, we are assuming that the flow is happening in that particular temperature. What changes here is the area of the pipe may change, the velocity of the flow may change, maybe at particular points the profile of the pipe may change. That is the area only, but profile and area, you get the gist of it. Whereas eta and epsilon, no, that new items which we derived, they change with characteristics of flow. Okay, which means these values are not constant value, they keep on changing. We already know that in turbulent flow, velocity values and pressure values keep on changing very rapidly. That's why we thought of using a particular equation, particular theory to derive an equation such as like this. But what happens even after deriving that, we are getting eta and epsilon which change with respect to velocity and diameter. We don't want that. We want certain constant values which we can depend on in deriving equation. That is why this equation does not have much of an importance in our engineering field. When you go to research fields who delve into higher research oriented studies and all, they have higher number of experimentations that they can consider and prove the validity of this expression. But when it comes to our engineering profession and engineering applications, we don't want such higher order, higher descriptive, difficult equation. We want simple yet concise and precise equation. So that is why this equation does not find its importance in our academics. What equation finds, that we'll discuss in the second part of this video.